Hey, my name is Felix and I'm presenting our paper, Cache Me If You Can, Accelerating Diffusion Models Through Block Caching. Text-to-image diffusion models can generate high-quality images from text prompts, but they are very slow. We propose a technique called block caching, which can be applied on most existing diffusion models and which makes image generation significantly more efficient. It does not change the underlying pre-trained model and only requires lightweight optimization. We test block caching on two very popular diffusion models, LDM and EMU, and we consistently achieve a speedup of 1.5 to 1.8x while maintaining the same quality. Diffusion models have revolutionized the field of generative AI. These foundation models enable many downstream tasks, ranging from image editing to 3D generation. However, one of the major drawbacks of these models is their high latency and computational cost. First, the denoising network tends to be very large in size. Second, the network has to be applied consecutively multiple times, starting from random noise to generate an image. In general, the more steps the network takes, the higher the quality of the final image will be. The research community has made significant efforts to speed up image generation. Some works aim to reduce the number of required steps by improving the solvers. Others propose to distill existing neural networks into architectures that require fewer steps or have a smaller footprint. While such techniques show promising results, they treat the unit model as a black box. This leaves a potential source of speedup, the unit itself, completely untapped, which is what we focus on. In particular, we focus on the behavior of transformer blocks, which are by far the most computationally expensive part of the network. In a transformer block, the input data Xin is first copied and retained in a residual connection. Then, spatial attention predicts an update Ci, which gets applied onto the input through summation. To understand the behavior of a transformer block, we analyze how the updates of a block change over the course of the denoising process, i.e. from one step to the next. We use a simple relative L1 metric between the current update and the update of the previous step. On the right side, we plot this development, averaged over a limited number of generated images. Every blue line denotes a single transformer block, and blocks are grouped by their position in the network. We immediately see that not every block behaves the same and that there are certain patterns emerging. For example, certain blocks are mainly active in the first half, while others are mostly active in the later part. Based on these observations, we hypothesize that if a block is not very active, i.e. the update Ci does not change much from one step to the next, then we can just reuse the update from the previous step and save the computational effort. This is the foundation of our block caching technique. To determine when to use cached values, we rely on the analysis from before. We define that once the sum of updates for a block exceeds a certain threshold, delta, then we recompute it. After the schedule is generated, it is fixed for all later inferences. Unfortunately, naively implementing caching can lead to artifacts. In this example, we apply caching to get a 1.5x speedup and generate an image. While the details are retained, the background now looks blurry. This is a result of a misalignment of the feature distributions between the cached and non-cached values. To solve this issue, we introduce a lightweight scale-shift alignment step. The parameters of this alignment are optimized in a student-teacher fashion, and the extra cost during inference is marginal. As you can see, scale-shift alignment fixes the artifacts issue. The image generated with caching now has the same visual quality as the baseline, while being significantly cheaper to generate. At last, let's check out some more results. We first show images generated by a retrained latent diffusion model. Block caching reaches the same visual quality while being significantly faster than the baseline. We also test our block caching approach with the state-of-the-art model EMU. Here, we show the setting in which we have a fixed computational budget. While the baseline can only perform 14 steps, block caching allows us to perform 20 steps at the same cost because it is more efficient. The results of our approach are of higher quality and contain more details. Thank you for listening. For additional details, quantitative results and more, please check out our paper and project page.